little hardcore. I'll be available. All right. So last time we were putting the mechanics back in quantum mechanics and talking about the quantum mechanical description of the dynamics of particles, which our players now are position momentum. Those are observables, and they have, we understand their connection that unifies the classical and quantum description is that momentum is the generator of spatial translations. It's the thing that's conserved if we have a spatially translationally invariant system. And so from that, we could say that because this is the generator, we wrote down a near identity form of the translation operator for a differential or very small translation as the identity and then a little bit generated by momentum. And so for a finite translation, that tells me that the translation operator is this exponential of that anti-Hermitian operator. And that translation operator acts as a unitary transformation that unitarily acts to enact this translation position. Okay. Equivalently, what we said, this generator implies that it must be the case that positional momentum don't commute. And that commutator that follows is the canonical commutation relation. Okay? Now, I should mention that we could kind of turn this around and look at it, if we just look at it, if I just look at the commutator in the other order, that what this tells me is that minus position is the generator of translations in momentum. So that the exponential here with the position operator in the exponent acts as a translation on momentum. Okay. So position is the generator, or minus position is the generator of translation momentum. Momentum is the generator of translation in position. Okay. All right. Given those operators, those Hermitian operators, we can write down representations by looking at bases. So the set of eigenvectors of position momentum are now represented by eigenvalues that are continuous variables. They can take on any real value. And so in that case, instead of a sum over discrete possible values of the vector, we have integrals over those eigenvalues that form the resolutions of the identity. Okay? And we can express then the representations of vectors in Hilbert space as now functions, complex functions, over the real line. So we now have, instead of a column vector in the representation, we have a function. And the function is a representation of the vector. Okay? And we have, in this case, two different representations, the position representation and the momentum representation. They are representations of the same state in two different bases, the position basis and the momentum basis. Okay? And this, since we have this continuum here, we don't, if we want to talk about a projection into some finite region, then this object represents a projection operator that projects the system into a differential region of the real line between x and x plus dx. So that's the projector in that slice of space. And so by the Born rule, what we know is that the probability to find the particle in that region is the expected value of that projection. And that is given then here. So that then allows us to interpret psi star psi, or the magnitude squared of that wave function, that probability amplitude, as the probability density to find the particle at x. Okay? I should say, we also saw here that the action of the translation operator on x ket is to translate the ket, and I can normally say the translation by momentum on the momentum eigenvector is to translate the momentum. Right, so the states thus are generally in a Hilbert space, and we want those states to be normalizable, and this inner product should be a finite number, and we typically set it to be 1. And that we can express in the position representation or the momentum representation. And so this thus defines the set of allowed functions that define the Hilbert space. The allowed functions are the ones that when I integrate them, the square of them over the real line, they must be finite, and that finite number we just then set to 1. So the space, the Hilbert space that we are discussing is defined by the set of complex functions over the real line which are square normalizable. And that set forms a Hilbert space. That's really what Hilbert space is about. Hilbert space isn't about, in some sense, 2x2 matrices. It's about this uncountably infinite set of functions and how they form an effective vector space with an effective dot product or inner product. All right? And that has a technical name. We call it L2 over R. It's square normalizable functions over the real line. Okay? We can look at, for example, now, so we have these representations, these wave functions. We can look at the representations in, say, position momentum space of these eigenvectors. Okay? So, for example, the position eigenvector, that's called size of x naught, the position eigenket at x naught. So I want to know what is the wave function in position space associated with this ket. It's the inner product of this with x, right? But that is this, which is 0 unless x equals x naught, and it's infinity, actually, if x equals x naught. It's a Dirac delta function. Okay? Or I could look at this guy in momentum space, the momentum space representation of a position eigenvector. We calculated this last time. That's given by this function, which is, of course, a plane wave. So if I were to look at, say, the magnitude of these representations, then a position eigenvector is a delta function localized at x naught. But in momentum space, that is completely delocalized everywhere in momentum. And this, of course, is not, this state is not a member of the Hilbert space. You can't ever prepare a system at a point. It would have an infinite spread of momentum. Of course, this is a reflection of the uncertainty principle. Of course, the opposite is true in momentum space. If I had a momentum eigenvector, then a momentum eigenvector, if I ask what is its wave function, what is that? That's a plane wave. So if I'm in an eigenstate of momentum, got the plus sign there, as a function of x, that's a plane wave. And we have this kind of pseudo-normalization. It's not really normalizable, but to keep it so that it has the delta function normalization, we have that factor there. So this is a plane wave. By the way, what is the wavelength of this plane wave? Usually we write a plane wave as e to the I k x. And the wavelength is, how is the wavelength related to k? 2 pi over k, thank you very much. Right? And in this case, k is p naught over h bar, right, for this. That is to say, p naught is h bar k. And so the wavelength here is 2 pi h bar over p naught, or the Planck's constant over p naught. This, of course, is the de Broglie relation. That a particle with a certain momentum has an effective wavelength given by Planck's constant over the momentum. Okay. Now, we were talking about last time the change of basis. So if I wanted to know, if I had the position representation, I wanted to get the momentum representation. Well, what I can do is a unitary transformation by inserting a resolution of the identity. Right? And this, we just said, was e to the minus I dx over h bar x. Or equivalently, if we want to go the other way around, I can insert a resolution of the identity with respect to the momentum basis. And this, of course, is nothing more than the Fourier transform. And as we discussed last time, we should think about the Fourier transform as effectively a change of basis. We're going from one basis, which is the position representation, to another basis, which is the momentum representation, or vice versa. And the change of basis matrix is the representation of one basis vector in terms of the other. Okay. Does anybody have any questions so far? So far, so good. All right, so what we're talking about here, thus, is wave mechanics. So wave mechanics is the way in which we talk about our quantum theory as described by wave functions. And we can think about those wave functions. Of course, Schrödinger developed this in the context of understanding what we knew about classical wave theory at first, but then we later understood this to be just a part of a more abstract theory of Hilbert space, in which wave functions are just one representation of an arbitrary ket, right? So let's see, what are our players here? So we have the position momentum representation. Wave functions. Now, if we were to talk, yeah.
Why is a basic change your ego from tilt to have a non-tilde x while x is tilde v?
Because that's a all right. So if we talk about, for example, the inner product between two kets, then that has an equivalent in wave function language. How do you project one wave function onto another? Well, we know how to do that. If we wanted to write it out by just inserting the resolution of the identity in X, and that is I take the complex conjugate of the function and I multiply it onto X, and that's equivalent to projecting phi onto psi. Okay? And that's what's going on here. If I wanted to find the momentum representation, what I do is I project my state onto the momentum eigenvector. And this is the momentum eigenvector, represented in position space. And it's got the minus sign because it's the conjugate. And that's how you remember it. Because the plane wave is e to the ikx. And it's, when you project, you take the complex conjugate. Now, of course, if you have frequency and time, it's the opposite of what we're going to come back to in a moment. But e to the minus sign when you get t instead of e to the anyway. Okay, so that's that. Let me get my notes here to make sure I remember everything I wanted to say. Right, and we have the normalization. Of course, we already broke it down. What about matrix elements? So suppose I have some observable A, and I want to write down that matrix element. Well, again, I can write this in the position representation by putting in resolutions of the identity. This is that. This is some function. And this is this. Now, what about those observables in position representation and momentum representation? We haven't talked about that. Let's do that. Let's talk about the position operator and momentum operator. In position representation, that's to say on wave functions. So, if I look at the position operator, what are its matrix elements with respect to x and x prime? Well, x on x prime it's an eigenvector. So this is, or the other way around. That's its matrix element. Well, what that means is that when x operator acts on a state, and I want to know what is the new wave function after I've done this operator. Well, that's this, right? This is the new wave function, which is x, because this is an eigenvector. And of course, if it's Hermitian, it doesn't matter if I go to the left or the right. So it's just multiplication by x. In the position representation, the x operator acts like position on outward is represented by x multiplying the wave function. What about the momentum operator? Well, that's trickier. If I look at the momentum operator, what is its representation between these two kets? Well, we don't know how momentum acts on this. All right? We know how it acts on momentum eigenvectors. So the way to deal with this is to insert a resolution of the identity. Right? I just did that right here. This is an eigenvector of a momentum operator. So this is the integral minus infinity to infinity p x prime p. Okay? This is e to the plus I xp. This is e to the minus I x prime. So this together is e to the I p x minus x prime over p prime. What the heck is that? If there was no p here, what would it be? That'd be a delta function, right? Dirac delta function. But this messes it up. However, what I can say is that if I take this over here is equal to 2 pi h bar over I, the derivative with respect to, say, x of e to the I p over h bar. Right? If I take the derivative of this with respect to x, it brings down an I h bar. Oh, sorry. To bring down the IH bar cancels that, I got a P. Okay, yeah.
Is there h bar on the log exponential into the IP exponential?
Yes, it is, thanks. Sure. So, what do I see here? Well, this tells me that this is equal to h bar over I times 1 over 2, or I'll factor out the 1 over 2 pi h bar. I've got an h bar over I. I can factor the d by dx outside the integral because this is an integral over p, e to the I p over h bar, x minus x prime, d by dt. All right? In fact, let me bring the h bar over here. This integral, if I change p as h bar k, this is an integral dk e to the ik x minus x prime, which is equal to it's a Dirac delta x minus x prime, and it's got a 2 pi. So, putting that all together, the 2 pi's cancel. And we have that this matrix element is equal to h bar over I, the derivative operator acting on the delta function. The momentum operator in wave function land is the derivative. And so we see that if I now ask the following question, suppose I have a state psi, and I operated on it with the p operator. So what's the new wave function? Okay, that new wave function is this. That's the wave function after I've operated with p, right? And again, if I now insert a resolution of the identity, this is this is equal to the integral h bar over I, the partial derivative with respect to x, x minus x prime, x prime. Now this, of course, this derivative is acting on this. So now I'm going to play a trick. First of all, this is a derivative of a delta function. What the heck is a derivative of a delta function? The derivative of a delta function is this integral. That's what it is. And it has a particular, it only makes sense inside an integral. In the same way that only a delta function only makes sense inside an integral. It is a tempered distribution, as we call it. Now, the way I can do this is I can make, this is an odd function if I change x to minus, if I change x and x prime as a minus sign here. So I can make this minus the derivative with respect to x prime. That's equal to it. This, I just used a chain rule inside. This is x minus x prime. And now I do integration by parts. Do you know what integration by parts is? Integration by parts means throw the derivative on the other side. That's what integration by parts means. If the surface vanishes, let's just say if I have an integral from minus infinity to infinity of the derivative of f of x dx, this is equal to minus the derivative of f of x, the derivative on the other guy, if the integrand vanishes at the endpoints. Forget about your UDV, VDU, whatever you learned in Calc 1. Forget it. This is integration by parts. Throw the derivative on the other side and put it on the x side. Okay, try it. So, integration by parts. Everyone should know it. So, in this case, I throw the derivative onto the other side and put a minus sign. So that says that this is equal to, with a plus sign now, x prime, this is, should be dx prime, pardon me, that's my dummy variable, x prime. Delta x minus x prime, h bar over I, partial x prime. And now, doing the integral, that says x equals x prime. So, in a very long-winded way, we derived what you know. The momentum operator in wave mechanics is the derivative with respect to x with this h bar. Right? So, what this says is that in position space, the action of the momentum operator in a state is represented by the derivative. Of course, we can do it the other way around. In momentum space, the momentum operator acts as multiplication by the momentum value. And the position operator acts as derivative, but with the other sign. Exactly the same way. So those are the representations of position momentum operators in wave function, in wave mechanics. Okay. Now the fact that the momentum operator in position representation is the derivative should not surprise us. The reason it shouldn't surprise us is that momentum is the generator of translations in position. Okay? Suppose I have some function of position, and I translate it by a small amount dx. Well, by Taylor's theorem, this is equal to the function of x plus dx times the derivative. In this case, it's one variable. What the heck? I'll just write it as a partial. It doesn't matter. It's only one variable anyway. That's Taylor's theorem. Right? And you f minus, or you just subtract it and divide by dx. That's the derivative, the definition of the derivative, right? But look at what that is. Let's, for fun, let me multiply this by I over h bar, and then write this as well, look at what that is. This is equal to f of x plus I over h bar times the momentum operator acting on that, dx. This is exactly what we wrote down. It's the infinitesimal generator of translations in position is the derivative. So the derivative operator is the thing that translates you in position by a little slope. So it's not a surprise that the derivative operator is a translation in that variable position. And I'll leave it to you to show that this thing which is the exponentiation of that, makes the whole Taylor series. That is to say, this translates you by an arbitrary amount. The first order thing is dx, and then you have second derivatives, third derivatives, and that's the whole Taylor series. And this is u minus I x e. All right. Very good. So we have, now in wave mechanics, we have wave functions, we have inner products, we have matrix elements, we have representations of operators. Let's talk now about the Schrödinger equation. So, the Schrödinger equation, the time-dependent Schrödinger equation, h bar over minus I, the partial respect to t of psi, is the Hamiltonian of psi. Now, what's the Hamiltonian? If we're talking about particle mechanics, then the Hamiltonian is kinetic and potential energy. So the kinetic energy is p squared over 2m, and then we have the potential energy. So, if I now write this in this is my time-dependent state. This is in the Schrödinger picture, right? So I can write this formally and just shove in a ket there, shove in a ket there, This is thus the partial derivative with respect to time of the wave function x and t. And then I have to have the momentum representation, the momentum operator represented in x is the derivative with respect to x. So this becomes 1 over 2m h bar over I squared, the partial squared, plus v of x acting outside. Yes, sir.
I mean, notice that, like, we just start off with psi of t,
Yeah.
but there's no t operator that you can smush onto that to a
No.
generic psi.
Yes.
It's already kind of like that, or?
So this is a subtle point that I never really delved into. What is time? How do we treat time in quantum mechanics? In non-relativistic quantum mechanics, time is just a parameter. It's not an observable. It's the parameter we treat as, at this time, what is the probability for this, that, and the other thing. So it's the arena, it's a parameter. There is no Hermitian observable. We can't ask, what is the time of the particle? Time is about, in non-relativistic quantum mechanics, is about us. At this particular instant of time, we ask a question, we do a measurement. What is the position? What is the momentum? What is the spin? So time is a parameter that parameterizes states in the Schrodinger picture, or parameterizes observables in the Heisenberg picture. But it's not an observable. Now, there's something weird about that, because of course in relativistic theory, space and time are interrelated. So what the heck? How can time and space have different roles? What happens in relativistic quantum mechanics? Does time suddenly become an observable? And the answer is no, position gets demoted. Position is no longer something to talk about the position of a relativistic particle. Now we'll come back, I mean, in some sense we measure time, I mean we measure it poorly in this stupid lecture hall, but, so we'll come back to that question. What does it mean to measure time? But from the point of view of the mathematics here, time is not a eigenvalue of an observable. It's just a parameter. Very subtle. Okay, so this thus is the time-dependent Schrodinger equation in wave mechanics. Okay. Let me just do a quick little aside. I talked about just the Schrodinger equation in this case, or we talked about representation just in one spatial dimension. Let's talk just quickly, we can write down the results in 3D. Okay, in 3D we have now position, which I'll call x with a vector. So this is x hat, y hat, z hat. And the momentum operator has an x operator, a y momentum operator. Okay, these are called vector operators. And we can have position eigenvectors which have vector numbers. So these are the eigenvalues. There are the three eigenvalues, x, y, and z. And these satisfy the same kind of orthogonality relationship now with a three-dimensional delta function, which is another name for delta x minus x prime delta y minus y prime delta z minus z prime. And we can have resolutions of the identity, but now integrated over x, y, and z. And we can have wave functions as a function of three-dimensional space, which are representations. And we can have normalizations. So now this is L2 and R3. And the action of the position operator on a vector in position space is multiplying by that position on the wave function. And what is the momentum operator in this case? How does it look in position representation? The gradient, right? This is h bar over I, the gradient. So in 3D, this is one spatial dimension. In three spatial dimensions, this becomes h bar over minus I d by dt. The wave function in three spatial dimensions is minus h bar squared over 2m, the Laplacian of psi plus v of x psi dt. All right, so finally, not finally, next, of course, we can talk about the time-independent Schroeder equation, which is the energy eigenvalue equation. Time-independent Schroeder equation is just another name for the eigenvalue equation for energy. And in position representation, well, the Hamiltonian is p squared over 2m is minus h bar squared del squared over 2m plus potential on psi is equal to E. Let me call this U, just to emphasize that this is not a general state, but it's an energy eigenstate with some eigenvalue. These are the energy eigenfunctions. Okay, so that's the time-independent Schroeder equation as a wave equation. Of course, we know that it's a simple case we can solve instantly, which you know, which is the free particle. have a free particle. That means no forces, no external forces. That means the potential energy is 0. In that case, the Hamiltonian is just t squared over 2n. And the Schrödinger equation if I rewrite it, looks like this. So I set the potential equal to 0 and just rewrote some stuff. Okay, what are the solutions to that equation? Well, there are lots of different solutions. By the way, this equation has a name. You know what this PDE is called? This is the Helmholtz equation. Has lots of different kinds of solutions. But there's one solution we can write down instantly, which are plane wave solutions. How do we know that plane waves are a solution? Well, they're a solution, we can just plug them in. Right, we could normalize them in some way. Where, if I plug that in, there's this Gaussian on this guy is minus k squared. So that means that k squared is equal to 2m e over h bar squared, or the energy is h bar squared k squared over 2m. We knew that from the start because, of course, for a free particle, the Hamiltonian, if I'm talking about a free particle, the Hamiltonian commutes with the momentum operator. Which means that the eigenstates of P are eigenstates of H, or at least there exists, as we know. We can always construct common sets of eigenvectors if they commute. There exist common eigenvectors. Let me write it that way because it's a subtle point that I'm going to emphasize in a moment. There exists common, complete, or common sets of eigenvectors of the momentum operator and the Hamiltonian. Okay. So the momentum eigenvectors are these, and they are eigenvectors of the Hamiltonian too, with eigenvalue p squared over 2m, which is equivalent to saying that the wave vector, h bar k, is the eigenvalue. Or I can say Now, I should note here that there is degeneracy. Why is there degeneracy? What set of different energy eigenvectors have the same energy eigenvalue? That's what it means to be degenerate. It means there are different vectors that have the same eigenvalue.
Oh, you're asking or?
Yeah, I'm asking.
Oh, the same magnitude momentum, but it's different
Exactly.
directions?
Exactly. So the direction is irrelevant. It's only the magnitude that determines it. So any plane wave which has the same magnitude of the wave vector, so the energy eigenvalue that direction. So what that tells me is just specifying the energy doesn't specify the eigenvector. Because it could be that plane wave, it could be that plane wave, that one. So how do we know? Well, as you remember, in our first weeks of class, we discussed that in order to fully specify an eigenvector, if there is degeneracy, we need to specify a complete set of commuting operators. So in 3D, we need three mutually commuting operators to fully specify the state. What are they? What are the ones that specify this as an eigenvector? Any suggestions?
And we're using momentum by two, right?
Could do that.
Can we use the spatial, like X, Y, Z?
That sounds good. What X, Y, and Z?
Uh,
Position X, position Y, position Z? That doesn't commute. Those aren't. But you're close.
Oh,
Momentum.
Px, Py, and Pz. They all commute with one another, and they all commute with the Hamiltonian. So that is, if we specify that, then the unique eigenvector, which is simultaneously an eigenstate, has the three eigenvalues. So the unique eigenvector, which is simultaneously eigenvector of those three operators, well, that state is the state which has these three eigenvalues, which we lump together in a vector. Okay? And these are the plane waves. That is to say, these vectors are plane waves, and typically we normalize them with delta normalization. We will see next semester another set of three commuting operators. If h is only a function of the magnet, I'm sorry, if this thing is a rotationally symmetric potential, spherically symmetric potential, oh, sorry, we're talking about a free particle, never mind. For a free particle, I have another example, because that is rotationally symmetric. A Hamiltonian, the magnitude squared of the angular momentum, and the z component. We will see that this is also, these three guys all commute with one another. You showed that in your first homework assignment, or second homework assignment, right? That LZ commuted with p squared, and L squared. So these three commute for a free particle. But they don't commute with momentum. So these are three different sets. And these things are, instead of plane waves, these are spherical waves. Spherical waves are also solutions to the Helmholtz equation. But they're not plane waves, and they're not eigenstates of momentum. They're eigenstates of this stuff. And these things have a name also, they're also called partial waves. And they're very important in the theory of scattering. We'll talk about that next semester. So, just because it's a free particle doesn't mean it's in a plane wave. If it's an eigenstate of energy, it could be a superposition of different plane waves, all of which have the same length of the vector but different directions. Any superposition of that sort is also an energy eigenstate, because you have degeneracy. And a superposition of degenerate vectors has the same energy eigenvalue. Okay. So, if I look at the solution to the time-dependent equation for a free particle, so if I initially start in an energy eigenstate, which is a momentum plane wave, well, we know generally the solutions are stationary states. They have that frequency. The energy itself is a function of the momentum, though. Okay. So my energy as a function of momentum is p squared over 2m for a free particle in a plane wave eigenstate. Of course, this is just the frequency of the wave. This is h bar omega. That's the frequency in time. Right? So this is e to the I p over h bar minus times divided into x minus the energy as a function of p. Or I could write this as, if I want to write it, in terms of the wave vector, k dot x minus omega k t. H bar k is just another way of writing it. Right? So that's a free particle. This is a plane wave. right? Now, notice the relationship here between frequency and wavelength is known as the dispersion relation. So E equals the energy relation using the wave-particle duality. Tells me that omega as a function of k is h bar k. That's the dispersion relation. For a free particle. And given the dispersion relation, we can talk about phase and group velocities. So the phase velocity how is that defined? Remember that? Those of you who took 406 with me, I got this in James.
Omega over K?
Omega over K,
Yeah.
right? It's wave theory. And so that's equal to h bar k over, or h.
Should the K in that dispersion relation?
Yeah, thank you, sorry. That's why I got screwed up. That was weird. That's right. And the group velocity is what? Thank you. Okay. Now, what the fact that this is not a linear relation means that the phase velocity depends on the wavelength. Okay? Here it is. Which means that different waves of different wavelengths move at different phase velocities, which means the wave disperses. That's why it's called a dispersion relation. Okay? Now, I ask you a question because this always confuses people or people forget. If I have an electromagnetic wave in free space in the vacuum, does it disperse? In the vacuum? No, because it's the speed of light, all frequency. It's only when you're in a medium. Whereas an electron, if I thought about it as a wave, an atmospheric wave, in the vacuum, it disperses because it has mass. It has to do with the difference between the dispersion relation. This is the non-relativistic. Right? For a photon, it's E equals PC. That's a linear relationship between omega and k. That's why this doesn't disperse, but this does. All right. So next, suppose that I look at this general case for the time-dependent Hooker equation in free space. or Porphyry Park. So I'm given this, which is to say I'm given a wave function at time t equals 0, and I seek the wave function at some later time. This is not necessarily an energy eigenstate. It's some arbitrary particle state. And I want to know, what is the solution? How do I solve the time-dependent Schrödinger equation? Well, a generic procedure is the following. Take the initial state, decompose it into energy eigenvectors. You know how every energy eigenvector evolves, and then resum them. Right? So my initial state at time equals 0 can be expanded in terms of energy eigenvalues. In this case, the energy eigenvalues are a continuum of energies. Energy goes from 0 to infinity, where the energy is given by that. Times that. I'll call this thing C sub P. And so my state at any later time is just that. Is that clear? So in this case, E and P are just related. So I could write this as an integral over momentum. Remember, the energy is P squared over 2m. So P is just the square root of 2m E. So I can equivalently write this as an integral over momentum. The magnitude of the momentum, e to the minus I P squared over 2m h bar times time. The momentum, these are my plane waves. So in terms of the wave functions, what this says is that the wave function at an arbitrary later time is the integral over all the momenta C sub P that's the solution. Where what is C of P? Well, C of P is this, which is the projection onto Fourier transform. It's the either minus I P of x or h bar equals 0. So what have we done here? what we say here is that, and I can write, this is really just another name for the momentum space wave function at time equals 0. If I know what the momentum space wave function at time equals 0, then I know what the wave function is at any time, because every one of these guys just gets a phase. If they're at time equals 0, these of course are equal, right? This is just the inverse Fourier transform. But at a later time, well, each momentum component picks up this phase factor. And this will generally lead to dispersion of a wave packet, also known as the spread of a wave packet. So if I start with a localized wave packet in position, because it has a spread in momentum, and because each momentum has a different phase velocity, the different momenta get out of step with one another, and the wave function will spread. And we'll review this in homework for your next assignment. All right? So, you're back to the future. We're back to wave mechanics. And it's all connected.